Hello and welcome to this video. In this video we're going to go through the gas laws. So far we've looked at how to define temperature, how to define energy using the zeroth and first laws of thermodynamics. We looked at the heat transfer that can take place in order to change the internal energy of a system, and then we said that we have to also consider how would we do work on the system in order to change its energy that way. Now, in order to do that, we said that we have to expand or contract these things, so compress it or expand it, and that means that we have to come up with some sort of substance that we can easily compress and expand. And the only state that is easily compressible and easily expandable is a gas. Okay, so this is why we're now going to start to investigate the behavior of gases. It is the only state which we know we can take any gas and compress it. We can expand it, we can heat it up, we can cool it down. All of these things just allow us to change the internal energy to be what we want it to be. And now we can then say that we can put variables on a gas that we can measure, and then we'll find that these variables will actually be able to tell us a specific state of that gas. And those variables are pressure, which we are going to note with a P, which is measured in pascals, volume, which we note with a V and is measured in meters cubed, and temperature, which we note with a T and is measured in Kelvin. Now, in order to get values for all of these things and put them so that we can define a certain state of the gas, we first have to think about how do these things affect each other. Are there any relationships where if I change the volume, I'm changing the temperature or the pressure or anything like that? And we call these our experimental gas laws. So these are laws that have been verified experimentally that work for any gas. Okay, so the first one that we're going to look at is called Boyle's law. And Boyle's law describes the relationship between pressure and volume at a constant temperature. So the way I remember the names of these things is that if I'm going to boil some water, I know that in order to change state, it needs to be at a constant temperature. So then I just say, okay, Boyle's law is the one with the constant temperature. And so I'm looking for a relationship between pressure and volume. So in order to investigate a relationship between pressure and volume, let's set up a real system where I just have a piston here that I can move in and out of this gas, and this gas is just consisting of all of these gas molecules. Now we have to think, if I were to push down on this piston such that I'm then going to compress all of these particles much closer together, the whole reason that I have pressure is because of the collisions with the walls. Pressure is caused by collisions, but only with the walls. Okay, so if I have these gas particles that keep colliding with the walls, they're exerting a force outwards, so they're building up a pressure inside this container. So if I were to then push them all together, they then are more closely compact, and they are now going to have more frequent collisions with all of these, with the walls of this container. And if I then have more frequent collisions, I'm then exerting even more force, so actually my pressure has increased. So I have this relationship where if I decrease the volume, I'm actually increasing the pressure because I'm increasing the rate of collisions. And this leads to the fact that these two are inversely proportional to each other, which we can write as PV is equal to K. So this is Boyle's law, where K is just some random constant. Okay, it doesn't have to necessarily be a specific constant, it's just a constant. Okay, so this basically means that pressure is inversely proportional to volume. If I decrease the volume, I increase the pressure. If I increase the volume, I decrease the pressure at a constant temperature. Then we go on to the next one along. So if I get rid of this space here, And the next one is Charles's law. And Charles's law describes the relationship between volume and temperature. So this is going to be at a constant pressure. So at a constant pressure, if I were to then say, I'm now fixing this system, and I'm going to say instead, let me have just a syringe, for example. Okay, so I've just got a syringe that has some end to it, and it's got this kind of plunger piston thing that has the ability to expand and contract freely as the forces act on it. Okay, so I'm trying to keep a constant pressure, so the pressure will vary as the forces act on this piston. If I were to then cool this system down, I know that I'm then going to actually decrease the space between all of these things, because if I cool it down, I'm reducing the total energy of the system, as we said in the heat transfer video. And if I reduce the total energy, I no longer have all of this kinetic energy from these all whizzing around. And so they're actually just going to be all compressed down to a smaller volume. So what I end up with is, if I increase the temperature, if I decrease the temperature, so I cool this down, all of this will shorten or condense itself to this kind of position, and I end up with a smaller volume. So if I decrease the temperature, everything contracts, I end up with a smaller volume. If I increase the temperature, everything expands, I end up with a bigger volume. And this means that temperature is actually directly proportional to the volume. So we write that as V over T is equal to K, where K again is some random constant, and this means that volume is proportional to the temperature. Now the final one is introduced with a few laws, by a few names. Some people will call it the pressure law, so we'll go with that, but I'll put in brackets here, it's also sometimes referred to as the Guy-Lussac law. Okay, so this is just a different name for it. But the pressure law then allows us to say that surely there's only one relationship left, that's pressure and temperature. So this is going to be at a constant volume. So we fix the volume. So let's say we have no container, we just have a box that contains a fixed amount of gas. And this gas, this container can't expand or contract, we keep it the same. So then we're saying, if I were to increase the temperature inside this box, if the temperature increases, what's going to happen is that I end up with much higher speeds of everything moving around. Okay, so I end up with much higher kinetic energies, and if everything's moving around much faster, I'm going to get more frequent collisions, my pressure is going to increase. And hence I have my third relation, which is that pressure is directly proportional to the temperature, so it has a similar relationship to the Charles's law. So pressure is proportional to temperature, volume is proportional to temperature, and pressure is inversely proportional to the volume. Now, all of these things are necessary, and we can actually combine all of these, because if we notice these proportionalities will be constant in any system, we can then say, what if we combined all of these and had just one equation that would explain everything? And to do that, we basically just say, okay, if we know that PV is a constant, but also V over T and P over T are also constants, then this whole thing must also be a constant. So what we can generally say is PV over T will always be constant. Doesn't matter what you do to the system, because if the pressure increases by some amount, then that means that the temperature increases by some amount and the volume decreases by some amount. So we end up cancelling out the overall effect. So the actual value of PV over T is always going to be constant. And for this reason, a good equation to kind of know is P1 V1 over T1 is equal to P2 V2 over T2, because this works for any gas, okay? Where P1, V1 and T1 are the initial conditions, and that means that P2, V2, and T2 are the final conditions. So they could give you a question, for example, that says there's a constant pressure, in which case you can cancel out the P's, and we say that we're going to increase the volume by a factor of 5, or the volume initially is 100 meters cubed, the temperature is 5 Kelvin. After, when the volume is increased to 200 meters cubed, what is the new temperature? And you would just rearrange for T2 and then solve given the numbers that you have. So you can use this equation to then go from there. However, when we are looking more in depth at materials like this, especially gases, things get very complicated very quickly because there are so many variables that can change because of all of the things that are present. We have not only got the energy differences, we have varying temperatures, we have forces acting on them, we have collisions between them, but we also have a lot of other things to consider that we haven't really gone into yet in A level. So what we then need to do is try and come up with a simplification. We need to try and condense all of these ideas by making a few assumptions that are going to make idea of how gases behave simpler. And this is what we know as the ideal gas law. Okay, so we'll start with ideal gases. So the experimental gas laws work for real gases. So these are gases that we'll actually have. So the room that you're currently in, full of gas, this gas in the room is behaving by these 3 laws. If you were to change the volume of your room somehow, you would be changing the pressure and the temperature. But for ideal gases, we have to make a few assumptions that make them ideal rather than a real gas. So we have to know these assumptions, and so we will list them and explain each of them. So the first assumption is that all of these gases move with random motion, okay? And with all assumptions that have to be made, there has to be some sort of experiment to validate that assumption. We have to prove that this is a random motion and that there's no kind of patterns or wind currents or anything acting in just a regular system space. And your evidence for this is called Brownian motion. And Brownian motion was an experiment in order to investigate whether gas particles actually undergo random motion. Now, the idea of it was that we can't physically see gas particles because they're way too small for us to see. But we can see smoke particles because smoke particles are quite large. They're made up of more things. So if we were to then say have a container that contained regular gas particles but also a few smoke particles, so these dots here, so each dot represents a smoke particle. If we then watch how the motion of the smoke particles changes within this gas, we can then validate this idea that they have random motion, because we know the motion of these smoke particles is going to be due to the collisions that they have with the gas particles that are present. And what you see when you do this, looking under a microscope, is that the motion of this will go literally wherever. They can change direction instantaneously, and the whole idea is to prove that we have random motion. So the motion of smoke particles is caused by collisions with the gas molecules. Okay, therefore, if the gas molecules are moving with random motion, they will force the smoke particles to also move with a random motion, because they'll keep colliding with them, changing the direction that it's traveling in. If we were to then say that the gas particles didn't have a random motion, we would expect that they would only ever be forced in one direction or the other, in order to then say you have some sort of pattern to the motion of these gas particles. So our first assumption is random motion. Our second assumption is that all of the collisions with the walls of the container are elastic collisions. Okay, so all collisions are elastic, meaning that we're conserving energy and we're not losing any kinetic energy. They're always just going to bounce off with the same speed that they went with. This also allows for the maximum amount of force to be pushed out on the wall, which means we allow ourselves for maximum pressure. The third assumption is that the volume of a single atom is completely negligible in comparison to the size of the container. And this is kind of obvious. If I had a room full of gas, I obviously know the atoms are going to be way smaller than the volume of the room. So the volume of the atoms is smaller than the volume of the container. Okay, and actually we should say negligible is negligible with respect to the volume of the container. Okay, and the final assumption that we make is that there are actually no intermolecular forces. Okay, this is our final assumption, because having no intermolecular forces is then going to, so no intermolecular forces, this allows us to actually rule out completely potential energy, because the potential energy is there based on the fact that there are interactions between these particles. If we have no intermolecular forces or intermolecular interactions between particles, we end up with basically no potential energy. And so we can actually kind of neglect the potential energy and just focus on the kinetic energy, since we could probably assume that the kinetic energy would be way bigger than the potential energy anyway. And so this is our ideas for ideal gases. Now the real thing that comes out of ideal gases is the ideal gas law. And the ideal gas law is probably one of the most useful things that we can use to approach gases. It's going to use the same proportionalities that we had before. So we're still going to use that PV over T is some sort of constant, but we can now put a value on what this constant is. Based on these assumptions that we make, we can do the maths, and we find that this constant is actually referred to as the number of moles times some gas constant that is found by experiment. Okay, so this then means that I can rewrite it the way that you have probably seen it before at GCSE. PV is equal to N times R times T, where N is the number of moles of the gas, and we'll look at the number of moles and what that means in a second, and R is known as the molar gas constant, which always has the same value, which is 8.31, and you can find this on your formula sheet measured in joules per Kelvin per mole. And so we can use this equation, PV equals nRT, to describe any ideal gas. Now, for the most part in physics, we assume every gas is ideal because it makes the math way simpler and everything then gets much easier. But this number of moles is kind of chemistry based, and we're not really chemists, we're physicists, so we can change this because sometimes we don't really care too much about the number of moles of something as much as we do the number of particles that we have. So we then need to look at a little bit of an explanation as to what actually is or what actually are moles. So moles is just a measurement of the amount of substance. Okay, so it's a measurement of how many particles you actually have, and by definition 1 mole of a substance contains 6.022 times 10 to the 23 particles or molecules, and this is your definition. This value here we know as Avogadro's number. And we refer to Avogadro's number as a big N with a sub uppercase A. And this refers to Avogadro's number. That means that if we want to get a number of moles, right, so our number of moles is N, this is going to be the amount of particles in a system, which is, we're just going to call N, so this is just the amount of particles that are present, divided by Avogadro's constant. So we're saying as a ratio of all of the particles that are in 1 mole, how many moles do I contain in this specific case? And so this is a way that we can calculate the number of moles in a system. Now, you can also say that the number of moles is just going to be the mass, or let's call it the molar mass of the thing. The molar mass is will be given to you in the question, and it's divided by the MR of the thing, or the relative molecular mass. Relative molecular mass. Okay, and this is kind of a chemistry thing. So let's go back to this just being mass for a second to make it a little bit simpler. And the mass of this thing now, we have to change because this is a very chemistry equation. Chemistry doesn't really work with big quantities like kilograms like physics does. So they tend to actually use grams instead. So actually in this equation, we have to remember that the mass is measured in grams. And this gives us our definition of what moles are. Now, I have a formula here for moles in terms of the number of particles. So if I actually want to investigate the number of particles rather than the number of moles, I can just substitute this value of N into the ideal gas law, and I end up with a new equation. I end up with PV is equal to N times R times T divided by Avogadro's constant. Now, from this, we can say R and NA are both actually constant values. So from this, I can then say I could just bring these together and get a second constant, so I don't have to keep writing this fraction. And actually what we find is that R over NA is K, which we're now going to refer to as the Boltzmann constant. And the value of the Boltzmann constant you can find on your formula sheet. To be K is 1.38 times 10 to the minus 23 joules per Kelvin. Okay, now this means that I can substitute in here, and that means I can either say PV is equal to nRT in terms of the number of moles, or I can say PV is equal to nKT in terms of the number of particles. Now both of these things are equally valid. We've literally just substituted one and then came up with a new constant, but these both explain the ideal gases. Now this kind of equation can also be used similarly to P1 V1 over T1 in order to just verify a certain parameter. If we could, for example, measure the temperature pretty easily with a thermometer, we can measure the volume pretty easily with a measuring cylinder or something like that. It's kind of difficult to measure the pressure, so we usually just measure the volume and the temperature, and then we just calculate the pressure as our final thing. So this gives us a relationship between these, but this only works for ideal gases, not for real gases. So this was kind of a long video, but this covers everything you need to know about ideal gases and experimental gas laws, and thank you.